Yeah, so this is a talk about program synthesis. It's joint work with Aditya Murali, Umang Mathur, Madhu Parthasarathi, and Mahesh Vishwanathan at Illinois. Can you hear me okay now? So it turns out program synthesis is decidable. And I'll talk a little bit about the problem for which that's true. And then I'll make a comment about why we bothered with this problem. It's pretty theoretical. And then I'll give a couple examples. And then I'll zoom out and you can see how we solved the problem. It's tree automata theoretic. So, like I said, it's mostly theoretical work, but we started this with the question of what would it take to get a decidable synthesis problem at all. We wanted the problem to be non-trivial, so we need an infinite class of programs, and we wanted to work over infinite domains, and we wanted to handle loops and if-then-elses. So that's where we're starting from. And where we landed was a setting of uninterpreted programs. So these are programs with symbols, function symbols, and variables, and they have assertions of equality and disequality between variables. And a program is correct if all the assertions hold under all interpretations of the variables, okay? So here's an example of what we're aiming at. We want to take in a grammar with some holes in it. So here we've got a while loop starting at x. It's iterating over some list. And then it's looking for a key k. And when it finds it, we want it to return the node. But we've got holes in the if conditional and then what to do afterwards. And then we're going to assert something at the end like x has the key k if and only if it was in the list to begin with. So the solution we would be looking for is something like this. If you're looking for the key k, and then you advance the pointer afterwards. So in our setting, like I said, these are uninterpreted functions. So here's another example, a little bit more in the syntax that we ended up dealing with. We got these two functions, enc and dec, for encoding and decoding. So you can take, in this example, we've got a secret and a key, and the encoding function gives you a ciphertext. And then this assume statement is basically saying we're only thinking about models where this is true. So this uninterpreted function decoder takes the ciphertext and the key, and it gives you back the secret message. So then at the end, we're saying there's this hole here, but whatever, presumably Z will get assigned to something in the hole. But whatever it gets assigned to, it can't refer to secret and it can't refer to key. So we're saying assert at the end that Z equals the secret, and we have a decision procedure that will then say this is actually unrealizable because there won't be a way to fill the hole for all possible interpretations that makes the assertion true. Another simple example, we're just checking if a variable x is equal to true, and then we're assigning this Boolean b to true or false, depending. And at the end, we want to say some variable y should be equal to b, no matter what happened, but we can't refer to x or b. So say we could assign y to true, but then there will be a model where x was false, and so we came here and b became false, and this assertion will fail. So you could do the other thing, the same thing with the other branch of the if. So this is also unrealizable. Now I'll explain briefly what this looks like in terms of our decision procedure for these kinds of programs. So we have grammars as inputs that have holes in them, and assertions are peppered throughout. And we build a tree automaton that takes program trees from the grammar. And we have this other procedure which does something that looks like congruence closure to keep track of equality information between variables. And it runs up and down trees and accepts correct programs with a minor caveat. They also have to abide by a particular restriction. And there'll be a talk later that goes into that by Umang. At the end of the day, though, we can intersect these two tree automata that are doing the two jobs for us, and then we can check emptiness and pull out programs that satisfy the assertions. So here are just a couple of the results we ended up with. The program synthesis problem for uninterpreted programs with this restriction, which is called coherence, is 2x time complete. And we also looked at transition system synthesis, sort of an uninterpreted version of that, which is x time complete. We have, actually in the case of straight line programs, uninterpreted straight line programs, so no if then else, no while loops, it's undecidable if you don't have the coherence. And then also we get that Boolean and recursive program synthesis are 2x time complete. So that's all. Thanks.
If the holes are actually not able to be satisfied with like a synthesis solution, will your program tell you like a model in which the variables like make it impossible? Just like for user feedback, if we want to like figure out what's going on.
I think we could find this information, but we haven't really thought about that yet.
Someone please ask another question so I don't have to ask a really tough question. Thank you. That was great stuff. So you said it's very theoretical, but so how much manual work is actually required to sort of either prove unrealizability or come up and fill a hole?
You mean like what does the decision procedure look like?
Well, how, is there a corresponding tool? How much of this is automated?
How much is automated? So we have an it's not implemented.
I see.
But we've been looking at what kinds of things can you do are there problems for which this might be useful? But I think for the synthesis stuff, we haven't really given it too much thought.